Alright guys, I'm just gonna play a little manhunt maze on a ratio. Right, this is growth manhunt maze. Let me turn up the resolution a little. And yeah, I'm just gonna play this. So there we go. Let's just figure this out. Let's play a little bit. And I just want to see what I can expect from this. This type of gameplay. I don't know. I'm doing this. This is sort of like a whatever type of video. I have no plans for this video. I'm just doing what I want, and yeah, this is one of the things I want to do. Alright, let's do this. I just want to play a little ratio. I don't know, to like warm up, I guess, because this is like brain rot, you know, like I'm just doing this for pass the time. Okay, so what I was thinking of doing for today's video was work on the thing I was talking about in the last video, which was MPitch, and I wanted to do that. You know, I just want to make a program that can utilize MPitch, and yeah, I want to make a program that can utilize MPitch. That's it, basically. Also, I changed my microphone to my headset mic, so it hopefully sounds a little clearer what I'm saying. And yeah, I hope you can still hear the keyboard. Like if I like tap pretty loudly, you can kind of hear it, and that's good enough for me. Yeah. Alright, let's see. I want to get that little thing there. Come on. I'm just trying to level up. I'm trying to see how long I'll last without dying. I want to see. I'm interested. Alright, now there's 2 players. There's another guy. This dude can kill me though, which is kind of annoying. Oh. Alright, I lied. I want to play a little more. I lied. So let's try arms race. Right? Or assault. Not many people. There's not many players on right now. Not many players. Let's see. So we have growth assault. Growth C. What? Nah. So let's try this growth assault. Which. Wow. Did you guys hear that? That was lightning. Okay, I actually don't want to play this. Just screw this. Screw this. Alright, let's boot up VS Code. So yeah, alright, I think I'm gonna continue coding this, since I'm gonna pick up where I left off from. First thing I'm gonna do is look on here, and let's see, maximum number of ones. Okay. Alright, so here, this is kind of what I'm looking for. So in the last video, I wrote this, the goal was to write this function here, and let's run it. Let's run it again. The music goes crazy. Alright, so let's go in here and let's do build run. And I think it's just gonna do this. Here I want to put the max. Yeah, let's do that. Yeah. Oops. Okay. Alright. So this is max. Max. Oops. Alright, let's cancel this, redo it. So for now, I want to check if this is working. So this is just working. Nah, but I want to see though. I gotta check string frequencies. I want to print out all the different strings, and want to see what happened there. So let's do I smaller than that. Let's do this. Is the current string length we are checking. Okay, so how do we do this again? I want to print all the strings. I want to print all the strings. Yeah, so how am I going to do that? I'm going to go in here. I'm going to call this num equals 0 and num smaller than 2 to the power of the length. And we should start at 1 for that. We don't have to, but I could. Okay, and so yeah, we have num. Okay, I'm gonna call this num string because that's kinda what we're doing. And I'm gonna call this string length to, yeah, to do that. Alright, so this is right there, and then we're gonna do this, and then we're gonna do that, I guess. And here I'm gonna check length strings. I'm gonna say this, and then here put string length. And so how do we do this? So I'll say frequency equals, and then we go into string frequencies and we do this basically. So the length, and this is the value. That's gonna be the frequency. And then I'll say num thing frequency. And then here I'll put the frequency. Here I'll put the frequency. So yeah, but num string and then frequency. And this should work. This should go through all the strings, and I hope I don't get a seg fault, but we will see. So yeah, we can see there. Most of the numbers don't have any frequency. So I will say here only print if frequency is greater than 0. So we can only print the ones that actually have something. Alright. Here we go. Okay, so mostly all of the strings are from length 6. Oh, just kidding. Length 5, we got more. Length 4. Okay, look at this. Yeah, so length 1 strings, we apparently don't have any of those. Which, that's kind of weird to me. But anyways, length 2 strings is this many. What I'm gonna do is add up all of these frequencies and then make sure they add up to the whatever it is. Okay, so this is kind of weird. We don't have anything for these, so length 8 and above, we just don't have that. And I don't know if that makes sense. Okay, I'll put tape. Yeah, this is the number I'm looking for. Maximum number of non-blank symbols at an N instruction Turing machine. Oh, what? Allowing any number of states. Okay, let's look at this. So it says no halt state is required. The machine never halts whenever the current combination does not have an instruction. This was added by some guy in 2025. So this is weird. Cross-reference. So he is talking about this. So what is this? Maximum number of non-blank symbols that an instruction Turing machine can leave before eventually halting. So I mean, we got 7. Which is like in between these two. And instruction 0, 1, 2, 3. We only checked up to the 3 state machines. Okay. I have questions. I have a few questions for this. Do we have to check all of the different states or just 3, for example? Because I think it said in the paper, and this also just makes sense, that this state contains all the machines for the states under it. Like all the 3 state Turing machines contain all the same behaviors of the Turing machines with 2 states and 1 state. Just because you could not use one of the states, you could choose not to use one of them. So I think I'm gonna try something with that. I'll try it out where like I don't check the 1 state or the 2 states. Maybe just I'll check 3 states and then see what results that gives. But what I want to do is I don't know. I think I want to do frequencies, you know, like output this somewhere into like a frequency table and then somehow like check the difference between these. I could do that. That's pretty simple. I just output this to a file and then that's it. Just output to a file. Yeah, I'll put can I do that? Yeah, I could do that. It's writing to that file, I think, using Linux Magic. I think, yeah, see, that's good. That's very nice. So that's our initial thing there, and the next thing I want to do wait, that's actually not what I wanted to add. I don't want that. What I actually want is the percent chance. Right, like not the frequency, I want the percent. Yeah, so to do that we would do convert these to floats, divide over the total number of strings. That will give us a percent. Let's put the F there. Let's see what we get with that. Let's see. Okay. So this is nearly 0. These are nearly 0. Which is crazy. Not really, but these have a higher percent. So this has like the highest percent, which is cool. Okay, so that kind of works. So I'm gonna put this in. I'm gonna call this. I'll just call it test 1. Just call it test 1. Alright, so I'm gonna let that happen. And then that's gonna go to a file, and then the next thing is I'm gonna start this on 3. Right, start it on 3, and then first I'm gonna see if it works. Yeah, it does work. Okay. That's gonna take as long as it does. Okay. And look at these percents. They seem to be very similar. But to make sure, I'm gonna put this in a file and then I'm gonna diff the two of them. See the actual difference. Probably, I don't, if there is no difference, then that's good, I guess. That would be cool. Alright, so we have two. So let's do the two of these. And there's a lot of differences. Let's try some, you know what, I'm gonna give. Can we do like a, can we just do this? Right? The power of the internet. So that's that, and then this is here. Let's find the difference. And they are all kind of different, but some of them are the same. Like this one is the same. This one is off by a teeny tiny amount. They're all off by teeny tiny amounts. 3731. I guess that makes sense. I guess that makes sense. These aren't. These are all the same. Yeah, that makes sense. That actually makes a lot of sense, because these first ones are generated mostly by the, or these are contributed by the other ones, the lower Turing machines, lower state Turing machines. And wow, they even generated some length 5 strings, right? Which is really not that crazy. But all these other strings they don't generate. They only do up to 5, right? Is that what that is? And is that, you know, right here? Because we got 0, 1, 2, 3. Non-blank symbols. This isn't even. That's probably not right. This is probably better. So we have 0, 1, 2. Okay, let me try something else. What if I convert the number into binary representation and print that instead, so then I could see that easier. Okay. Alright, so let's do convert num to binary array. Let's do that. So this is gonna okay, quick problemo. This is a C thing, but I have no sense of, I don't even know what I'm saying. Alright, anyways, so yeah, you're gonna put in the number and the buffer that this is gonna go in. I think it's as simple as that. And let's say max buffer size for safety reasons, so we don't get any seg faults. Alright, And this is going to return true or false if it went overboard or not. And yeah. And, yep, we're going to do this. And here we're going to do a for loop, I guess. And we're going to be doing things with the buffer. Right, and but before we do that, we are going to should the buffer be like a char buffer? I think it should, just because that usually makes things easier. So how do you use memset? It's the value and then how many bytes. How many bytes are we gonna do? We're gonna do this many bytes, right? When do we use memset? Yeah. So I'm gonna do this just to make sure we don't mess things up. So here I'm gonna check if the number is greater than a certain amount. So that amount is gonna be 2 to the power of max buffer size. So if this right here, if number is greater than 2 to the power of this max buffer size, then we know it can't work, and it's going to do a seg fault, so we just return false. But if it does work, then we go ahead and we do our thing, which is we clear the buffer, and then we do our stuff here. So what do we do here? I don't know. So number, how many bits do we use here? I think it's just gonna be this. I think we can just do that. Alright, so we're gonna do a little bit manipulation stuff. Yeah. So I'm gonna do, it's gonna be lowest significant bit or whatever it's called, like the right is gonna be the biggest or something. What should I? This shouldn't be buffer size, right? Max. I'll call this max bits. How about that? Let's call it max bits. Let's yeah. Whatever. Okay, so yeah, actually we're gonna start at max bits -1, and then every time we are greater than or equal to 0, I'm gonna decrement. So what we're gonna do here is buffer I equals, and this is what I'm gonna do. So we're gonna go into the number, right? And we're supposed to and bit mask and one shifted. Okay, I actually don't remember how to do this. What is it? Like, so we have our number and then we get the thing shifting throughout the number. So the number, how do we do this? How do we do this? I don't know. I don't think it even matters where I start, so I'm just gonna go back to the original, make it less confusing. Okay, so we go to the buffer, and so what we do is we do like a bit mask with one shifted left as many times. So we have to use like something weird with I. So we shifted 0 times. Now we're gonna do this. Right? Is this what we do? I don't know. Yeah, I don't know. So we're gonna go check it online with the good old C Online compiler. Good old C Online compiler. That's alright. So yeah, alright, we're gonna define the nope, and we're gonna define this. Yeah. Okay, so we are going to do a string. I'm gonna call this the buffer, and this is gonna be 10 bits, I guess. No, I'm not gonna use 10 bits. I'm gonna use 9 of them, and then the last one will be the null terminating, just so I can print F the thing. Alright, so that's what we're gonna do, and we're gonna put this here, and we're gonna put in a number, put in the buffer, and put in max bits, and here we go. Yeah, we didn't include string. I knew that was gonna happen, guys. I knew that was gonna happen. Alright. Okay, so that didn't work. Let's put parentheses around it, so just so we know. Okay, so that's not how that works. Is this? This is a binary array, so we can't just print it out as a string. It's all zeros. Okay, I think I'm gonna have to do Mr. For loop here. So we got max bits, and we are going to do we're gonna print. We are gonna do that, and that should be good. Yes, let's put 3, and there we go. What? So buffer. I think this has to be an OR. Nope. What is that? Negative? How? Negative 12 or something? Okay, wait, what if I put a space? Yeah. So this messes things up. What? So the buffer. What if I do... What if I do a different... something different? So I go like this, and I shift 1 left all the way to max bit -1. What the hell, bro? And then we go right I bits. Is this how we're gonna do it? So this starts at 0. Yeah, I mean that kind of makes sense. It's the same thing. What? I mean it's all 0. And then we do num. No, I think we do have to do and. Oh, so this is working. This is actually working because if I do 1, that's right there. If I do 1 1, like binary 1 1 1, right? Let's bring up the calculator. Let's just put a bunch of 1s. Yeah, 255 for example. Why did I just go crazy with that? Okay, yeah. So it goes negative because it overflows. And if I do 8, so it's 8. So 1 2 3 4. 1 2 3 4. Okay. And I put 9 bits. So this is the 9th bit. I think I can just put a 9 there. Print 0 to... There's 1 2 3 4 5 6 7 8 9. Why is this 0? Oh, just because. Yeah, so if I put 511, does that not do it? 511 max bits. Maybe it's because I did -1. No, actually. No, actually. Is this why? So it returns false? No. So we start at 0, and then we go this many times. Do I do plus? No. Do plus 0, plus 1, -2. What the? -2. Is that correct, even? What if I did 4 bits? Alright, and I did 15. Okay, that worked. There's a 0 here. Kind of weird, right? How there's a 0. Now this looks better, but I don't know why that. What's the big deal here? What is the deal? Okay, what if I do this? Okay, this is kind of weird how it turned out like that. Because we're starting at buffer 0. Right. What? And then we do buffer max bits. And then I put it in a number. Okay, that didn't. What? How is this nothing? Oh, it probably returns false. 6 bits. Yeah, this is 8 bits. Let's test that out. Let's do 7, 8. 8 should, well, 8 shouldn't work actually. There we go, see? That works. But it like doesn't do the last one correctly. Okay, well, it's not that it doesn't do it incorrectly. It's just that that's the max number of bits. So the actual number is from 0 to the max bits. That's the actual number. Okay, that makes sense. Also, the number itself, I don't want it to be the number. Okay, what if? So like I'll do that, and then what I'll do is I'll shift it all the way back. Okay, this is weird. So what did I do? So the 1 is shifted, and then I shift it I number of times. So the first one is going to be, so it's going to be num thingy, and then I have to undo this, I think. Okay, this is turning out weird. That didn't do anything. Okay, what if, well, hold the phone, hold the phone. So what is this doing exactly? So first we do this. We do 1 shifted left, max bits, -1 times. So that's a thing, right? And then we AND that with the number. Okay, this just seems kinda wrong, but not really at the same time, because what if I do this? What if I do this? 191. Because look, it actually works, because I got a 1, is the only 0 is right here, which is this one. So it's actually getting the correct bits from number. Like if it's 1, it turns into the 2 to the power of whatever place it's in, but if it's 0, it's just 0. So yeah, but the problem is I don't really want to do that. So I think what I gotta do is this, maybe. So I get number and it with the thing, and I think I have to put it all the way back. I don't know why I did I here, to be honest. So this is just kind of weird. What am I doing here exactly? So the number, we AND it with the 1 bit that is shifted. Okay, what if we do this? So that doesn't work. This does work. Because this is being shifted. So first we do the 1, shift it all the way to the left, and then we shift it to the amount. So it's starting, the 1 is just starting all the way in the left, and then we just go right for as many times we do. So we start on this one, and then we go second iteration, we do this, third, fourth, fifth. And this seems to be working. But yeah. Okay, so I think I have to shift this new number. Wait, do I? Yeah. So I gotta shift this new number back to the beginning. So into the first position, so it's either 1 or 0. So yeah, we gotta do that. It's some combination of these 3 things probably. So what is it? We do I, or we shift it. You know what? Let's just. Let's just start typing things. Oh, that. What? That was correct. That was correct. Let's try 0. 1, 2, 3, 4. Well, that was just correct. That's kind of funny. Yeah. That's so funny. Okay, well, this works. Let me see the difference. What did I do differently? So the only thing I did differently was this part, which I had to figure out. So I did this, which was pretty good. But then I had to start like iterating through the different code. You know, I feel like this could be smaller somehow, but yeah, I don't really know. Rightmost bit is lowest. So if we do num, excuse me. So if num equals 3, and max bits equals that, the buffer would look like this. So we would have 1, 2, 3, 4, 5, 6. right? Isn't that max bits? Yeah. So this is what it would be, and then the buffer. The rest could be whatever it is. Yeah, so if I did this, do 1, 2, 3, 4, 5, 6, and then the right bit is the lowest. Okay. A little documentation. Yeah. So what was I doing that for? Oh yeah. I was gonna use that here. So instead of putting this here, I'm gonna make a print array binary print binary array. Why not? Why not? Alright. So we're gonna do that, and then we do that, and it's just yeah, it's right there. Look at that. Great. It's gonna be great. So we don't need to do that. We can do that. So print binary array. We can do that. So let's do a thing. So let's do print binary array. Let's do a buffer of 10 thingies here. Well, it doesn't matter, we can just do that. And then here we can say, we can do buffer, and then how many bits do we want? What is it, string length? Let's do string length. And then what I did here is convert number to binary array num buffer bits. So we're gonna put the number buffer and bits, which is gonna be that. Alright, so we're gonna do that, and I'm gonna do this, and I did an error here. It's complaining. Let's fix that real quick. Yeah. Alright. Okay. Is it good? Look at that. Looky that. It actually, this is much better. It's showing us the binary instead of like the thing. So this is cool. We can see now all the percents. I don't know if we want to, if I want to, what do I do? Start at 1? Do I start at 1? Yeah, so I'm gonna just keep doing all the Turing machines, I guess, up to like from 1 to 3. And yeah, I mean, this is so funny. This is so low, it's actually like, it's actually 0. It's actually like pretty low. But maybe I should put a double instead of float. Maybe we'll get higher accuracy. Is that a thing? Can I... How do you print a double? Yeah, it's an LF. That's what I figured. Alright, let's do this again. Let's try to get more accuracy. More accuracy. Okay. So we still get 0. Is that not correct, Amundo? So what? For print, so this is a double anyways, so I don't even think this matters. Print F. More precision on floats. Okay, how many significant digits for doubles? Alright, so what was it, point? So how many do we have here? 1, 2, 3, 4, 5, 6. Let's do 10 Digimundos. 10 Digimundos. 10 decimal places. Maybe that will increase it. Precision. Yeah. Okay, I can't tell if this is actually accurate or not, but I don't know. Alright. Something I do want to do actually is still include the frequency, just so we can figure that out. Yeah, so let's do that. Alright, so pretty soon, I do want to try to make this quicker, or read the paper to implement CTM and you know, the coding theorem method. So yeah, so now that I got this code up and running with this kind of infrastructure where I can get the frequencies of all the strings and enumerate the Turing machines for 2 symbols with 2 actions, and yeah, so that's good. That's cool. I like that we can do that. So that's cool. Okay, so this is I'm pretty satisfied with this code. I'm gonna go back to this, try it again. So the coding theorem method is right here. So frequency counter, right? Frequency counter. We do have the frequencies of said strings. Is this how simple it is? So we just do the frequency and then the negative log plus a constant, which I do not know how to get that constant. How about this? How about this? So enumerating Turing machines. So they use something else. They use the natural numbers and yeah, so they do stuff. Oh, I just cracked my neck. Yeah, that kind of makes more sense to do, to be honest. But I didn't do that. I didn't do that. So, okay, here's what they do. They do reduced enumeration. So there's they say there's many symmetries. God damn it. I don't want to do these symmetries. I just want to check. Let's see. Give the result running all machines. Alright, I don't really care about that, to be honest. I want to check this out. So the coding theorem method. Okay. So there's short strings. Yeah. How do you wait? How do you actually do compression with this? Okay. Once a machine produces it for the first time, one can directly calculate an exact value of K under this model. Okay. What's M? What is M? Every string produced. So that I'm guessing that's the term. Oh, here's the thing. This is kinda weird. So we have two. So the frequency. Oh, because the frequency. Okay. Let's look at the stuff there. I want to look at this again. So I think we need to write this down. So here they're saying the M, whatever M is, what do they call that? Universal distribution or something? The algorithmic so this is, okay. So this is plain complexity. So as long as we use a universal in a Turing complete model, then it's gonna be good. Yeah, so in practice, C can be arbitrarily large. Okay. So this is algorithmic probability, and I remember it was in here as well. Yeah, right here, algorithmic probability. Well, not right there, but so if we look at this, so it's 1 over, we just add up all the thingies from 1 over 2 to the power of the okay, that's interesting. And so they're saying that the length, let's erase these real quick, and I'm gonna put this into that file just so I can look at it. So they're saying, yeah, so this is a universal distribution. Probability that a random program which halts and produces S in a universal Turing machine T. Okay, so that kind of makes sense. That makes sense. So here are all the strings that are a thing. I really want to optimize this, but before I do that, I think I have to figure this out first, just so I can do it. So this is the universal distribution, and equal to this thing. Okay. Okay, what? So they're saying that the distribution here is kind of equivalent to this, which kind of makes sense because we are iterating all the programs. No, actually, that I remember. I think he said this. God damn it! All right, gotta cut the video short, guys. All right, I'll see you guys in the next one. Peace out, buddies.